have liked on this whole Fourier stuff. And we have looked quite a bit yesterday on numerical integration. So today, I think now at least, I would like to focus on the problem of reconstruction. So, signal. So just to recap from yesterday, the goal is you have at some points here, you have sampled what the values of some function are, and the goal is to find f of x that best explains the data we have. And of course, if you didn't have any prior on this, then you might have drawn for these points something like this. If you have some prior that it is not spiky and it's fairly smooth, you might have drawn the red curve. And if you were here discussing this about 40 years ago, you would have done this, right? Which is what the statisticians call linear regression. It's widely used. We're just calling it signal reconstruction because now people wanted it to sound more fancy than regression because everyone did linear regression. And the signal processing people wanted to show that this is not linear, and they said, so we call it signal reconstruction. But essentially, they are the same thing. Okay? And now, of course, we have pretty sophisticated nonlinear regression tools. So you might as well call this regression. And if you're searching for any new results, remember to search for both, because the signal processing community is stuck with signal reconstruction and the statistics community calls it regression. Okay, so in either case, you see, you may not stick to the data points, right? So if f of x passes through all data points, then we call this interpolation. Okay? But in general, your regression need not be interpolation. You can have an approximation of your curve. Okay? And f of x is called the interpolant or approximand. Okay, anyway, so this is the simplest sort of way to describe what signal reconstruction is. Of course, you can do this in higher dimensions. You may have different priors from different sources and so on, which may help you in your regression. The classical way that people did regression was to pose it as an optimization problem. So they said you want to find some f of x so that maybe you minimize the least square distance or something to the points, right? That's least square minimization. Or you could frame it with other sort of optimizations. And the signal reconstruction people started thinking slightly differently from that, and that's sort of how it diverged. Right? So the signal reconstruction people, as we saw now, all these products of functions and convolution theorem, so they said, okay, let's look at this whole process differently. The idea is you have some function f of x that we know is the ground truth. So if you have a microphone that is recording sound, that is how the pressure waves are. We will never be able to measure exactly what the pressure waves are. But if you have a very good microphone, you will be able to sample this at some times. And the microphone may give you very close to the curve. It may give you a set of points. Okay, so what they did was they represented the function that we don't know as f of x. They represented the sort of sampling function as sfx, for example, and said, okay, so this sampled function is, okay, let's call this, the sampled function is the red one, is equal to the original function multiplied by, you will see this often, a train of Dirac functions, right? Which is usually written as a Shah function like this. So I'm just going to write it as a sampling function where S of x equals this. Now each of these is a Dirac delta. A Dirac delta looks like this. Spike at 0, right? So delta of x minus xi shifts the spike. So x minus xi means the spike moves to xi. So if you have a sequence of xi, then you have a sequence of spikes, and if you add them all, you get a signal that looks something like this. Right? This is x0, x1, x2, x3, and so on. And this signal can be written as just S of x. And if you multiply this signal, remember these are all Dirac deltas, you multiply them with f of x, you get this red signal here. Right? And the red signal looks something like this. It's like the Dirac delta train, but it has different heights depending on what has been sampled. Now, once they saw this, and right, if you see this now, and now that you know what the convolution does, we're pretty excited, right? We're like, oh, this means I can immediately write down what the dual will be. Right? We know the dual is going to be convolution. Right? We saw this convolution here. So this is the sampled signal. This is the signal that we want. And this is the sampling signal. And by looking at this, they said, oh, let's see what happens, right? So now if you knew, for example, that f hat omega was band limited, right? Okay, let's leave that alone for a bit. Let's maybe look at convolution. Okay, you're going to do that Gaussian thing for homework. Let me just show you one image so that when I now present it, so there was this. So you can read this at home, but just to give you some idea, what happens when you convolve. Okay, so we have f, which is the blue curve, g is the red curve. When we want to find the value of the function at the dashed point, you see this dashed here, that is our omega. Okay. So as for every omega, we would like to know what is the convolved value. At each point, you multiply the areas in the product of f and g. So till this red box, which is g, hits blue, there's no intersection. So the product is always going to be 0 there. Right? So the convolved value is 0, 0, 0, 0. Until it overlaps, in which case f times g becomes non-zero. And as it slides, the overlap becomes more and more, and then becomes less until it slides out of this blue, right? So now if you trace the value, 0, 0, and you can see this thing going up here, the area is increasing till there's maximum, then the area comes down. This result is the convolution of that blue box with the red box. Okay, now here's a different signal. That's an easy signal because you have two boxes, you know exactly what the area should be, you know it should be linearly increasing as you slide down. Now here's a more complicated signal. You have f and you have g. You slide g. As you slide g, you see what the intersection area is, and you keep plotting that. And you see that curve there, and that fall off tells you what the convolved value is. So now the intuition I want you to have about this for the next bit that I'm going to talk about is that you have two functions f and g, and you're sliding one function across the domain. The center of that function is what the convolved value is going to be. Until you have some intersection, it's going to be 0. As soon as you start having an intersection, you're going to multiply both and integrate. Multiply both and integrate as you slide. Every point as you slide, the multiplied and integrated value gets recorded. That's the convolved value. And you do this over the domain. If you've done image blurring with the Gaussian kernel, that's exactly convolution, right? What would you do? You would take an image, take some pixels, convolve it, multiply the kernel with that square patch, take the sum, and then record it at the center of the square patch. It's exactly the same thing in 1D. Okay, so Gaussian blurring of an image, if you're more comfortable with that, is nothing but a convolution. And that's exactly what's happening here as you slide this window. Obviously here, because one of the functions is a square box, it looks like it's fairly easy. And if you notice, that is not g of t, that is g of t minus tau. Like we had before, you look at what we had. Above here, right? You see, we had this g of omega minus omega prime, which meant that this was our reference, and at every point, when omega changed, one of them would slide. So in this case, I took f with respect to omega. In that case, they're taking g. But as homework, I would like you to make this connection between what I have written. And the reason I wrote this is because this is the straightforward interpretation from here. But then you can connect it to what is the more intuitive explanation, which is very commonly found. This is much easier to visualize and understand. Okay, so now with this sliding stuff, let's go back to where we were. Right? What we want is the convolution of these two. Okay. Now, if I choose, now in this case, the xi's are all over the place, right? There's some 2 here, and then there's 1 here. It's not regular. If I choose, if xi equals k over n, right, where k is increasing, or what was my variable, I over n, oh, this is a mess. I shouldn't choose I anymore. Let's choose k. I don't want to confuse it with a complex, right? So if xk is equals k by n, then what would happen is you would get regular samples, right? Each of them will be separated by 1 over m, so it's regularly placed. Now it turns out, if you go from minus infinity to infinity, you get this really long train. Okay, it turns out that the Fourier dual of such an S of x is the same function with different spacing. Okay, so S hat of omega, if this is the case, then S hat of omega equals a Shaw function of omega, which means that you will get back the same type of function for S hat. And again, you can go and read about this. It's a well-known thing. It's easy to derive as well. But the distance changes, right? So this is x that has omega as the domain. Obviously, if these two spacing, if the spacing here is reduced by increasing n, what will happen to the dual? The spacing between them will spread out. Because what it means is as these are closer and closer, you need very high frequency sinusoids. So the spacing in the Fourier domain will push it out towards higher frequencies. So that's sort of how you think in the Fourier dual. I won't show those things because we will run out of time to do all of that. But yeah, so now we know this is a Shaw function here. This is often called a Dirac train or a Shaw. Shaw is with a W function, right? And you know that there's a train of impulses, right? This Dirac delta is an impulse. Now, this is nice because what it tells us is this is one of the functions in the convolution. Okay, so now let us see what that convolution would look like if one of them is a Dirac train. So we have, this will be at DC, 0, and you have all of these things, right? So to make things easier, now if you look here, because there is a sum, obviously if I add a lot of Diracs as n goes high, it's going to be messy because the sum will have some integral, and we already said before we would like to normalize things, so I will divide this by n just to make life a bit easier. Okay. Now if you divide this by n, what would the integral of S of x be? Each of the Dirac deltas integrates to 1. If I integrate the sum by n, then S integrates to 1. Okay? And an interesting thing that I didn't mention with the Fourier transform definition there is if you look at f of 0, where was that? Sorry, just one sec. I should have said this in the morning. If you look at f hat of 0 and you substitute 0 here, then this goes away. You simply get integral of f of x. Okay, this becomes 1, so you get integral. So the 0th frequency, which is called the DC component because it was studied originally for power and that signified for electric current and signified DC, is 0. Is the 0th frequency, which is just the integral of f. So if you come here, if this is S hat of omega magnitude, then this is the 0th frequency. So what is the height of this? It's going to be 1. You can imagine, right? Okay, now if I have to convolve this with f hat. So let's say f is a Gaussian, and f hat looks something like a Gaussian. It is a Gaussian. Then how do we then do this sliding thing, right? Because what we want is f hat convolved with s hat. So for now, let's assume that this true function is a Gaussian and you are sampling that Gaussian by multiplying it with the Dirac train. Now what will happen is we would need to take f hat, okay, slide it from here, multiply it with these values, add that thing. So because these are Diracs, it's easy, right? If you have a Gaussian there, I'm giving you the answer to your homework already. If you put a Gaussian there, what will be the product and the integral of the product between the red and the green? It's simply going to be this value here. If you put a Gaussian here, it's simply going to be that value. Because obviously there's no overlap outside that, right? So everything else will be 0. You'll only get that value. So as you slide the Gaussian, this value is what you would put at the center of the Gaussian, right? At each of these places. So this value will get copied here. This value would get copied here. And you would trace out some kind of curve. And as you slide one further, so let's say the same Gaussian goes past like this. Now you have two values. You have one here and one here. This is the center of the Gaussian. So you will add this and this, and you will get some value here. So your curve will be the sum of those two, right? If your Gaussian is very narrow, what happens is you may not get a huge contribution for both at any point. If your Gaussian is wide, then you'll get contribution. If your Gaussian is really wide, you may get contributions from many of them. But it's very easy because you just have to evaluate the Gaussian at each of those points and add them. So the integral becomes easy. Anyway, if you did that, right, what you would end up getting is some kind of function. So I'll draw the result. You would end up getting something like this. At every peak, you will get the peak value of the Gaussian. And as you slide away, it will start reducing. And then it will start gathering some from here and so on. But it will again go up at the next peak. Is that clear for you to see? It's exactly the sliding thing I showed you on Wikipedia, except now, instead of a instead of two boxes, I have a Gaussian and I have these Diracs. So as you slide the Gaussian, you can imagine the product increases, and when it aligns with this, it's the peak. And as it slides off, it decreases until it hits the next peak and so on. So the final thing you get will look something like this, right? It will be the sum of all of that. So it will look something like, okay. So now if you see this orange curve, which we got here, which is the sum of those things, is Fs hat omega. That is what we sample. So what has happened is, from a single Gaussian, by virtue of our sampling, we have now got Fs hat omega as the spectrum. So if we took the inverse Fourier transform of f of s, we wouldn't actually get back f. Right? It's just like the image. We took the image, modified the Fourier transform. So obviously, if you take the inverse, you don't get back the same image. Similarly, because we modified, here the modification is the multiplication with the sampling code. Okay, now you're asking, okay, if I take the inverse Fourier transform, will I get it back? No, you wouldn't. So what should you do now to get back f? But the obvious thing now is we can do the trick that we did with the image. We can say, oh, look, there's a nice Gaussian here. That looks like f. Let me just chop and throw everything out. Right? So I could easily say only take this part of the signal. And what is this called? A low pass. We saw already, low pass means let only the low frequencies through. So now we're saying we're going to take this sampled Fs, we're going to apply a low pass filter, and that should give us back, what should it give us back? F, right? That's the easiest thing. When will this fail? This fails when these things are, so obviously it depends on the bandwidth of the signal. If this Gaussian instead of a Gaussian, so if this has really very high frequencies, then obviously each time it is here, it will gather from all over there to there, right? Which means the values here will contain information about all of these other peaks, right? These are called copies of the spectrum. Because of the sampling, we have copies. And because it is a copy, it's called an alias, which means it looks very similar to this. It's just an alias spectrum. Right? So what happens is, if the aliases are really wide, because my original function was very wide band, then the aliases will all contribute towards the signal here. Right? However, if we squeeze the aliases to be very low, very tight, then what would happen? Like we did, right? We squeezed, by drawing a circle, cut everything out. We've squeezed everything into this small band limited area. Then we can guarantee that if it is band limited, each of these aliases will never touch this spectrum. Okay, and obviously there is a sweet spot, right? If you can guarantee there is a minimum, maximum radius to f hat, then you can guarantee that if my sampling distance is greater than that maximum, I can guarantee that these peaks will never affect my central spectrum. Is that clear? So this is a very key concept, and we're going to extend this later, so it's important that you understand. Okay. Does anyone want me to repeat it? Okay, I'll still say it again. These are all peaks caused by this f hat being multiplied with these spikes. Now, if f hat instead of this was a wide Gaussian, then every time you placed it, even a peak here, which is so far away from there, would have this wide Gaussian, which will contribute and mess up this region. And if that happens, when I apply a low pass filter, the content here also represents the signal that was here. We don't want that. We want the content here to represent f hat only once, not multiple times. Okay, so the point is, keep these red spikes as far possible, or squeeze f hat as much as possible. Right? Now, what does it mean to keep the spikes really far away? So there are two options now. Option 1, keep red spikes far away. Or 2, squeeze red f hat of omega to be narrow. Right? If you do these, then after low pass, you obtain perfect reconstruction. If you guarantee that you have squeezed this really low or spread the spikes far away, then you're guaranteeing that there's no other element of these alias copies in this. So when you do a low pass, you get the perfect signal. Okay? Obviously, this only works if f is band limited. If f is not band limited, it can have frequencies to infinity. So no matter how you push this, unless you have pushed it all the way to infinity, you're going to get some aliasing. Okay? That's the intuitive side of this idea. Okay. So this is a very sort of basic result, a fundamental result in signal processing, right? Which says if a signal is band limited, then you can perfectly reconstruct it, provided your sampling rate is greater than 2 times the max frequency of f, if the signal f. Okay? And this 2 comes from here, right? So basically you want to chop off at half because you don't want this color to touch. And again, if you push the spikes far away, it means this is, remember, this is f hat, s hat, right? So if you push s hat out, it means you want to pull s, squeeze s, right? Which means your sampling will now be very, very, very close. So if your microphone is sampling at a very, very, very short time duration, then in the frequency domain, it's sampling at very high frequency, then this spike will be at very high frequency. That's why you need to sample really fine if you want. If your acoustic signal is very high frequency, so for example, if you're listening to music with hi-hat cymbals or high frequency sounds, then your maximum frequency of the audio signal that you have, maybe very close to the hearing limits of the human system, then you will have to sample really fine, right? You have to sample at twice that frequency. If you want to if your sound has 20 kilohertz, you'll want to sample at 40 kilohertz. And your microphone, if you sample at 40 kilohertz, you can guarantee that everything in your signal is there. Assuming that you're sampling regularly, right? This is all assuming that you have regular samples at every. And this is called this is the sampling theorem. It's called Shannon-Nyquist. You can find many variants of this. I'll just put the terms there. This is called the Shannon-Nyquist limit, or rate or limit. Different communities use different terminology. But the idea is you have to sample at some max rate. Now, if your signal is not band limited, then all bets are off. You cannot guarantee that you get a perfect reconstruction. Okay, is that clear? Probably all of you have seen the GIAN and Nyquist thing, but I think this view of it helps when we analyze integration. Any questions? Yeah. For band, what do you mean by band pass? It's just the max. It's always the max. It doesn't matter where. Same condition. So if your maximum frequency is not bounded, then you can't guarantee perfect reconstruction. If your maximum frequency is bounded, it doesn't matter what else happens inside. You need to sample at that maximum. Right? Because anything else will cause. So this pollution of central replica of f hat of omega by alias spectra is known as aliasing. So you probably all heard of aliasing. What happens there is nothing but saying that this part that I'm going to clip out is polluted by this alias copy. So if your sampling is too wide, then this will become close. This will come closer and closer there, which means this alias will overlap with your reconstruction. So once you do a low pass, it will contain information about alias spectra, and it's called aliasing. Yeah, it really doesn't matter, right? And yeah, that's an interesting thing. So when it was originally proposed, it was only proposed for regular sampling, right? If you're doing stochastic sampling, how would you do this? You would have to look at the Fourier transform of the samples. And if you can guarantee that the Fourier transform of the samples satisfy this, it's a slightly modified version. Right? I don't think anyone has stated it that way. But it will, when we do integration, I'll show you that yes, for integration people have thought about it. Yeah. Okay. Good. No questions? Okay, so now we've done Nyquist theorem. Okay, so now we've looked at a bit about signal reconstruction. We saw integration yesterday. We saw how we measure error in integration. How would you measure error in reconstruction? Any ideas on how you can measure error? So obviously, if you have aliasing, then you have error. If you satisfy the Nyquist rate, then you don't have error. But if you don't, or if your signal is not band limited, or if for any other reason there is error, how would you measure the error? Obviously, once you reconstruct, so if that is f, like our brick example, you may get f of x, and this may be f inverse of, okay, this, let's call it the f reconstructed of x. And you want to measure the error. You can do many things. You can subtract them, take the norm, right? So you just do fx minus fr or take the norm. So that's depends on what your error metric is. So there are different error metrics to quantify quality. And this is very application dependent. Because imagine you're recording sound, and I tell you the L2 error between the reconstructed signal and the original signal is 0.32. Really means nothing to you, right? You listen to the music, if it sounds totally distorted, then you say this is not good. It doesn't matter whether it's at that point 0.32, 0.032, minus, to the power minus 4, whatever. So that's a very application specific thing, because humans are very perceptive to these kind of distortions. Similarly, visually, we are very perceptive to any distortion. So you may have a very, very low L2 error, but sometimes you look at an image and you think that just doesn't look good. And it's very hard to quantify this. So these are perceptual metrics, right? So sometimes you have perceptual metrics to tell you whether things are good. And that complicates things a lot, right? Because you may have very good reconstruction from an L2 point, and you optimized it with some really complicated optimizer, got to really low point in the objective function, and then people look at it and say, no, it's not good. Then that means your objective function needs to account for perceptual metrics. Then you need to understand the perceptual side of things. So it becomes very, very difficult. So that's a big challenge. And for music and sound, so people did psychoacoustic studies, came up with good metrics for both compression. So we have MP3, MP4, all these things, where they looked at what we consider as perceptually jarring artifacts, and they tuned this. And similarly for visual, we are very, very sensitive to aliasing. And I'll show you some examples where this alias copy just looks terrible, even though, if you use an L2 metric, it may not be very, very jarring. Okay, so that's just a quick note on error for reconstruction. Now let's also recap error for integration. Now already you've done some histogram and so on, right? Remember we had this estimator which was f of xi divided by n, where xi were drawn uniformly in 0, 1, right? This is what you did in your lab yesterday. Draw xi uniformly, you got a uniform histogram. Now mu n, remember, because xi are random, mu n is also random, right? Every time you run this, you get different set of xi, you get a different mu n. So mu n is a random variable, which means you can start asking what is the expected value of the random variable. So this is expected value. I'm going to use this. And you can ask things like what is the variance of this random variable. This is the estimate of the integral, right? This is the estimate. And we're asking questions of the estimate as though it were a random variable, because it is a random variable. It's a combination of random variables. Xi is a random variable. F of xi is a nonlinear warped random variable. And then you have a linear sum of these. In the end, you get a random. So what will happen is you can now plot a histogram of mu n, just like you plotted a histogram of x. Okay, the law of large numbers tells you that you will end up with, in this case, if you plot it, you will end up with a Gaussian histogram. So the histogram will look like a Gaussian here. Roughly, obviously there will be noise and all that. Just like you did yesterday, you will end up getting that kind of a histogram. And there will be some mean. Okay, now what is this mean going to be? What is the mean value, or the expected value of this estimator? Is going to be I. Which is the integral, right? We saw that for an unbiased estimator, this is going to be I, and obviously you have some variance associated. So if you plot a histogram of the estimates, you will get a spread centered around some mean. Now, if you have a biased estimator, what will happen? Oops. If you have a biased estimator, you will still get some Gaussian distribution, but the mean will not be I. And there's the bias, right? So this is the bias. However, you may be able to design a biased estimator with very low variance. Yesterday, when you increase the bins, number of bins, you got very high variance in each bin. Variance is not good, right? Because it looks far from the result you want. Whereas in this case, variance is very small. So you're thinking, oh, that's actually a pretty good estimator. I get very low variance. However, it's biased, it's far from the original answer. But this may not be bad. For many applications, variance is more important. So for example, if you're doing something quick, interactive, maybe it doesn't matter that, yesterday's case, you just want something that gives you low variance reasonably quickly, and then if it is not tending to the exact answer, you can always run something else, get a better estimate. So depending on what application you're looking at, you might want either low IIS or low variance. Obviously, if both are high, then it's useless. If both are low, that's great. So these are the error metrics for integration. Okay, any questions? So now what I'll do is we've looked at both of these. So I'll go into presentation mode here and just recap from yesterday. So if you remember yesterday, this bit I'll just switch off the lights. Is it visible at the back? Or do you want me to switch off the light? Is okay? Okay. Okay, so you remember that recursive equation, and then we sort of, oh, okay, it doesn't work. Never mind. We rewrote that and I explained the bounces, and this was for the light paths, if you remember, right? Now let's see where reconstruction and integration show up in computer graphics. So now, so far, we only looked at theory, and again, as I said yesterday, it's an example in computer graphics, and there may be some similar examples in your field. So let's say this is f of x. That is my ground truth image. Okay, it's very, very high resolution. It doesn't look like it, but let's pretend that's a small part of the image. And this is fx. You see, fx has some really, is binary first of all, which means it has some kind of box structure on every row, and there's some weird skew as well. Okay. Now imagine that this part of the image we want to reconstruct, but we only have 9 pixels at our disposal because it's a part of the image. Okay, I don't want to use 100 pixels or 1,000 pixels. I want to represent that image with a 3x3 grid. What would be the simplest way of doing this? Simplest way of doing this would simply be place your 3x3 sample here and then see what is the value here. Is 0? Copy it, make it 0. If the value is 1, copy it, make it 1. Simplest. This is what we did all this time. We had a Dirac delta at each of these. And if the delta times the function was 0, you get 0, otherwise you get 1. That's the simplest thing. Here's what aliasing looks like. Because in this case, the function here has very high frequencies, and because our sampling rate is very low, what has happened is that the spikes are very low. In the red spikes in the Fourier domain are very close to the origin, and the function has a very wide Gaussian or spread. So when we do that, there's a lot of pollution by, you see there's nothing here. So frequencies, you can start seeing at some point, you start seeing all the artifacts from aliasing. Okay, so there was some sweet spot where so I intentionally chose this example where the frequency of the signal as you go up is changing. And you can see at some point you feel, okay, it's okay till there, but not beyond. That's basically your Nyquist limit. Okay? And it's very obvious when you look at this, there's something jarring about it, right? But if you compute an L2 error, it may not actually look bad. It may look pretty decent. Right? So now let's change this idea a little bit. So let's assume that for each of these 3x3 samples, now there's some square patch surrounding them. So we're not going to take a Dirac delta anymore. We're going to take some region around it. And instead of simply copying the value of the function, we're going to add a small 3x3 grid there, average the values of the function. And instead of putting the center value, we're going to average these 9 values in each of these. So in the end, we still get a 3x3 grid. So in terms of sampling, we have sampled it. There's a little computational expense extra, which is adding this 3x3 grid, right? And then you get this result. Okay, so what have we done here? What we've done here is we've replaced these. So if this was the function, right? Instead of sampling like this, we're now saying, this is my function. Instead of this, I'm going to store this integral. And this is that small patch. Okay, in the limit, I didn't draw all of them because then you can't shade them properly. In the limit, all these areas are abutting, right? Like here, they're all abutting. So what have we done? We have taken the sampling function. So here the sampling function was this. Here the sampling function well, it's not really like that, because if you multiplied these two, you will not get this, right? So now instead of sampling f of x times s of x, which we did there, here we're doing f of x convolved with s of x. That's what the averaging is. We are sliding this 3 by 3 grid along. At each point, we're multiplying the two signals and adding them up for averaging, which is an integral. And we're recording that integral at this point. Then we move along, record that integral at the center, and so on. So we are convolving it, actually. So instead of the previous case where we did this, now we are convolving both. Okay. So if we're convolving, so in this case, the Fourier dual was f hat of omega convolved with this hat of omega. What is it now? Because this is a convolution, it will become a product. F hat of omega product with s hat. They're just duals, right? So if you multiply here, it becomes a convolution. If you convolve here, it becomes a product. And this makes sense, right? Because if you look at the product, this is exactly what we did when we took the brick image, put a circle, multiplied by zeros outside in the Fourier domain. Then we got some blurry convolved version. That's exactly what we're doing here, right? We're multiplying this by some filter and we get back this. And now you see the result. It averages out a lot of the. And you may ask, okay, but this doesn't represent faithfully the signal. But it turns out for certain perceptual metrics, you may want to choose this. Still not great. But there's the other thing is, we just average the values. You can choose different weights for the averaging. And that means that you're basically saying, I want to shape this filter in Signal processing language. You're saying, I want to shape the reconstruction filter for each of these so that I get the best aliasing, the least aliasing. Okay, so now let's look at this from a slightly higher dimensional perspective. We have our 3 by 3 grid. In the end, we want a 3 by 3 pixel. We have some function here, which may have high frequencies. And we're going to, from this function, deterministically filter it to get the alias-free or minimum alias reconstruction. But remember that we don't actually have that function when we do computer graphics. What we need to do is to estimate light transport, like I showed you yesterday. So that function, which is the black and white function I showed you, was just for illustration. In practice, that function needs to be estimated by performing transport simulation. So we need to take photons, transport them through this whole thing, get to the final, so let's say looking at this statue, that color at that statue is f of x, that value, right? And the funny thing is, here, when we do these estimations, we're going to use Monte Carlo here. For integration, we're going to use reconstruction here. Both need to be done. Monte Carlo results in an estimate of the function f, which has noise. It has errors. Because of the stochastic sampling, you have errors. So this would be a nice case where we just know f of x. In practice, we have to reconstruct without even knowing f of x. We will only know f of x around with some noise, right? Because of this integration. And we add up all the estimates over different light paths. So we have multi-sampling for the reconstruction filter. We have multi-path sampling for numerical integration. And in the end, in computer graphics, we want to do both. This is what makes computer graphics a bit tricky. But it also is what makes computer graphics a field where both of these need to be studied hand in hand, not just as individual problems. And actually now, as we've seen results here, we start realizing that in many applications, these two problems exist. And people may not have identified this very clearly because here it was very obvious that you have an integration problem, you have a reconstruction problem. Oh, actually they're decoupled, but the coupling is this function f. In many applications, it's very hard to do this decoupling. And I think that itself will be a valuable contribution. So if in your field, if you think and see if you have both of these problems and are able to decouple them and show this, it's very valuable because people may apply tools from different techniques And you may actually even find interesting results at the interface of both. Okay. So if you look at this sampling, let's look at a function space view. So as I said, there are many light paths. Now each of these light paths is in some high dimensional space, can be thought of as a point. Okay, this light path, you can think of it as Google Maps telling you, go from campus here to the railway station, right? When you go from campus to railway station, you're at campus and this is the railway station. It tells you, go to this junction, take a left, and then you go in 18th Cross, and then you go to Majestic Central, and then you do this, right? So that's sort of a path in your map, which you're very familiar with. And you may have different routes. And what this is saying is each route in this space can be seen as a point. There's some high dimensional space, and there's a mapping between these routes and this space, which is not relevant for now. Okay, and I'll just show it to you as a two-dimensional space, but it's actually some high dimensional space. And here are our three paths, which are now points. Remember, each of those points is some route. So this is one way of getting to the railway station, this is another, and that's another, okay? What we need to do first, if you remember that diagram with integration on the right, is we need to integrate. So we need to project all of these pixels, we need to integrate. So at each of these points, we need to integrate all the paths. So there's the integration problem. Once you do that integration, remember the Buddha, the statue in the middle, that function f of x can be estimated using this integral, right? Now these dots here are telling us what the radiance value is. That's the integrated value. And what we want to do is reconstruct the yellow signal. So the goal of computer graphics is to efficiently project here and then reconstruct. Okay? And if you don't understand computer graphics, that's okay. Go away with the high-level view that there's an integration which results in a signal which needs to be then reconstructed. Okay? And obviously, all of these things, I said, you could use information about local behavior of the function. So for example, if you remember the f of x with the black and white stripes, each part of the image had different behavior. Some places it was like that, some places it was like that. If you look at the Fourier transform, it will only tell you what the image as a whole looks like. What you actually want is local Fourier transforms, right? Or some representation where locally, around each point, you know what the variation is. So for example, if they tell you, and this, coming back to our example, going from here to the railway station, you have one path in that space, and somebody asks you, oh, you're going along this path, what if they block this road? If they block some road there, you're going to take some detour and go back to that path, or maybe not even go back to the path. This local variation will tell you how easy that is. Because for some places, like if you're going through Cubbon Park and they've blocked one of the roads and there's no other road through the park, if they blocked it, you have to go all the way around. So example is somebody came from Bangalore, right? And now because of the floods, there's one road blocked. You have to take an alternative route, and it was through the Ghats, which means the local variation here was telling you that really there is no chance of any other alternative route, go far away. Then you need to explore faraway spaces. Of course, for this, you need to have a notion of what is far away, and you know what is distance, what is the distance metric, and so on. But if you can store this local variation amongst these samples, then what happens is when you do the integration, you can use this information to project. So for example, if you know that there is really nothing above or below, then projection is easy. You just put it down there. It's an approximate projection. You can use this just like we used the bandwidth of the signal to decide what the sampling rate should be. If you know that the bandwidth is like this, then you only take the samples that are relevant to you, or you only sample as appropriate. And for each application, this is a very, very difficult problem. And computer graphics, so we had a couple of papers doing this for a very specific case. Okay? And as you can see, I've listed many papers that take this approach. So this is the general idea, and there are different ways they've engineered this. And you can see they're not that recent, but they're not that old either. So in the rest of this course, actually what we're going to ask is, how can we use this Fourier information to make a sensible analysis or to derive something useful regarding the sampling. So for example, we would like to know what is the mean squared error of our integrator, what is the bias, variance, for example, what happens to the convergence rate of the estimator, and so on. And since Fourier analysis has been a useful tool for analyzing signals, even though it may not be a useful tool for image processing anymore, as useful as before, it is still a very powerful analysis tool. And we asked the question, so it was 2013, we asked the question, oh, why can't we use this to analyze integration? Prior to that, my co-supervisor, PhD co-supervisor, had written a tech report as well on this. He had thought about this. And another person who was then at UC Berkeley, also Ravi Ramamurthy, he also had thought about this, and he had written some things on it. So we all kind of had different views of this. And I'll present a few of the views. And then so one of my postdocs and another student then published a paper which followed up, and now there are some recent results on this. But the general idea is this: you have many points in this space, you have some information about local variation. From there, can you say anything about whether this integrator is going to be useful or not? Okay. Yeah, so now the question is, I remember why I had this, right? So you have different points here, and every time you take a random sample, you get different sets of points. And those sets of points will have to need to know what the local variation for those points are, because it's a stochastic process. So the question is there an easy way to kind of tie all of this stuff together? Okay, I think maybe we can do another 5 minutes. Is that okay? Yeah. 12:15 is when I was supposed to stop. So if we go back to our problem, this rendering problem, just to give you a high-level perspective, we have one pixel, which is the image sensor location. We ask the question, what is the radiance arriving at the sensor? Okay, you could think of that as how many vehicles are moving through here per unit time in a particular direction. If you're at some junction there, you want to know what is the density going this way, right? That is your transport analogy. And this is obtained by doing some high-dimensional integration. Okay? This is a very high-dimensional. As we saw before, it's typically infinite, but you can truncate the series. And so this integration is over shutter time. So if you have a camera, shutter opens and closes. If the shutter is open for a long time, then you have sampled over a long time and averaged, right? Because all the photons that have a... So there's an integration over shutter time. The aperture area, obviously you don't have a pinhole camera. It has some small aperture, which is finite. Some good cameras, you can open up the aperture so that you get more light. But once you open up the aperture, you need to integrate over the aperture, right? And then the first bounce, second bounce, which I explained. So there's some high-dimensional integral. So in this case, you have two balls. This is a rendered image. One of them is moving. And because the shutter time is quite long, you can see the blur due to motion has accumulated. This one is out of focus. It's in front of the plane that is in focus of the camera, which means it gets integrated over the aperture as well. Okay, that's not relevant. What is relevant is that there's some integration going on. And we've already looked at this 1D integration problem, right? And I said, you can look at the 1D integration as a product of this and the sampling function. You multiply them. Similar to our reconstruction problem, you can look at it as what we did yesterday, the Monte Carlo estimator. Now, again, we're looking at the sampling function, which is not different from what we did for reconstruction. We could modify the weights associated with the samples, as we did with our reconstruction. We could also modify the locations, obviously, with random sampling. We could modify the location. And we talked about jittered sampling yesterday, important sampling, quadrature rules, which we also talked about. Now, why are we analyzing all this in the Fourier domain? The problem is, if you did this, the mathematical machinery you need to analyze the result of this sampling will be something. And it would be different if you modify locations. These two approaches will require, of course, you can do both in conjunction, but this would require very different mathematical machinery. So we asked the question, what if we looked at this also? Vijay's question was actually quite interesting. I hadn't thought about it before. We only thought about integration, right? So you asked the question, in reconstruction, why can't we look at the Nyquist rate and see what happens if you have stochastic sampling, right? What we did here was we said, for integration, how can we reconcile the two? We have regular sampling and variation. We didn't look at it for reconstruction, which would be interesting. So we said, if we now look at the Nyquist rate, which was for reconstruction, first of all, then try to see what it means for integration. But in addition, we also want to use the same framework regardless of how you modified the samples. It seemed like a natural choice. There's results in the Fourier domain. And let's first see what those results would be if we're doing integration. So obviously we used Fourier, and now we've looked a lot at this Fourier stuff. Yeah, so that's this is all nice. So we can take a function that's the sum of exponentials, and then we can write them out, just like we did. And we've already done this, so I'll skip it. We've done this. These are in the slides, so it will be easy for you to look them up, but they're not relevant. What is relevant is, if you now take a sampling signal, right? And you take its Fourier, so this is the same sampling signal we looked at before, right? Except there's no 1 over n here. And you take its Fourier transform. Then you will end up with some phase and some amplitude. Looks like this. And that is your S hat of omega. When we did reconstruction, we had a Dirac delta train. In the case of the Dirac delta train, this was very easy. It was simply the delta train itself, but scaled differently. Once we move the positions, now this becomes a bit tricky, and it's very related to Vijay's question, which is, oh, okay, now that we don't have a Dirac delta train, can we say anything about aliasing? It's funny, actually, that we didn't think about aliasing in the reconstruction. We kept thinking about, oh, how can we say anything about integration? So that's the sampling spectrum. Well, remember that if you're stochastic sampling, if you're using stochastic sampling, these things are random, which means this is a random variable. This is a random variable as well. So for any sampling instance of 4 samples, you will get some pattern like this. But in general, you may get different values. So if you break that down, each of them is a Dirac. Okay? If you think of what the Fourier transform does, it takes this Dirac delta. Again, this would have been very easy to explain if you had already read about the stuff yesterday, but let's assume that you have, and you can go and read it today. If you have a Dirac delta and you apply the Fourier transform, at each frequency, it gives you a real and a complex value. So this is the real and imaginary complex plane. It gives you a real and an imaginary. So this is the point that that delta function gets mapped to. Now you can look at the amplitude, which is the distance to the origin, and the phase, which is the angle, right? And I've plotted the amplitude and the phase. Now you can map this at different frequencies. At each frequency, that will result, the same delta will result in different points. So you will get something like this. And because for the Dirac delta, it happens to lie on a unit circle, we know the amplitude is always 1. And we know for that particular function, you get a linear phase. Okay, so it would look something exactly like that with appropriate numbers. And if your original sampling function was a linear combination of these, then you get a linear combination of these. It's fairly simple, right? Everything's linear with the Fourier over. The Fourier transform is linear, it just spreads over them, you get for each of these. This is really interesting because each of those samples gave us a pretty flat, uninteresting spectrum. However, when we add them all, because they're complex, and again, this is why I said very important to remember that this is complex, and the signal processing people actually didn't do some of this stuff, which, because they always looked at amplitudes and didn't look at phase, because phase is very tricky. You get a very different view. So now if I'd thrown away the blue values and only used amplitudes, if I'd averaged the amplitudes, I would get something highly uninteresting. Just get flat. Gives me no information about anything there, because the only information this pattern carries is where they are located, which is exactly what phase does. They're all located on the unit circle, but they're located at different points in the unit circle. So unless you average them in that two-dimensional complex space, you're not going to get anything interesting. However, once you account for phase, you will get some rich spectrum. And this will be a pretty good representative of that. Okay? So if I threw away phase and only looked at amplitude like we've done most of this talk, then I will not get something interesting. Right? So just to reiterate, you have a random set of 5 samples. They will all map to different points on the unit circle at a given frequency. Obviously, as you change the frequency, they will map to different 5 points. And now you can think of the centroid, right? When you add them, average them, you have 4 or 5 different at a single frequency. You can think of this centroid obviously now having a different amplitude than any of those. If you had thrown away phase and only averaged amplitude, you would get just the unit circle back, which is not interesting. Now you get this centroid, and if you remember, it's a stochastic process, so you have different instances of the same spectrum. You can take an expectation over it. You'll get some expected centroid, and you get some variation around that centroid. So what we've done now is we've taken a sampling strategy. We've abstracted away everything that was used to generate those samples. Instead, we're saying blindly apply on multiple realizations of that strategy. Just draw one realization, compute its Fourier transform, draw another one, compute its Fourier. Repeat this many times, you get this idea of an expected centroid, which is the expected spectrum, and some variation around it. So now instead of thinking of, so let's now look at the amplitude only. Let's throw away phase to simplify. So we have to cut a compromise. We don't want to keep phase till the end. So now let's say at that point, we don't worry about where this dot is. It could be here, it could be here, it could be anywhere. We're just looking at the amplitude, which already gives us much more information. Yeah. So if you do different samples, for each sample, each instance, you will get one orange curve, right? For each, so this instance has 5 samples. You draw another instance of 5 samples. So each realization has a set of 5 samples, not just one sample. No, same strategy, yes. Yes, we are analyzing a particular strategy. Yeah, if they're from different strategies, you can't do much. So they all need to be. That's why I showed them like this. Right? They're realizations from the same strategy. Okay. Now you will have an orange curve for each realization. You have some idea of what is the expected amplitude and what is the variance in the expected amplitude. Right. So now this is really handy because we can throw away anything you knew about the strategy. For now, you can disregard whether you modified weights, whether you modified positions, none of that stuff matters. The only thing we're going to look at is what is the expected spectrum, and then ask the question, in terms of the things now we know, expected amplitude spectrum and the variance, can we say anything about the error in integration? So to highlight Vijay's question, what we're saying is we have one sampler, we get different realizations of n samples, we have different realizations of the associated spectrum. Now we ask another sampling strategy to give us n realizations, maybe with different weights or whatever the strategy is, doesn't matter. And we take its n realizations. Now we say forget about the samplers and all this stuff. Let's focus here and look at these and say which is better or which has certain properties. Obviously now we need the metric, and we already looked at if you plotted histograms, you have a reference value, you will get some bias. So you can use either bias or variance. And in computer graphics, high variance looks like this, because at each pixel you could get a very large value or a very low value, and then you see these speckles. High bias might look like this. Right? So if you remember, the original image was a smooth blur. This is very structured, and that is noise. And perceptually, some people argue that one is better than the other. Anyway, our point is not to make a judgment on what is better. What we want to know is, can we analyze both bias as well as, yeah, I think that's a good point to stop. But what we want to analyze is what happens if the spectrum has certain properties and the variance of the spectrum has certain properties. What happens to variance? What happens to bias? And then an application, for each application, people can look at it and say, oh, in my case, I want variance, so I want low variance, so this is better. Okay, that's the whole point of the analysis. So have I covered everything? Actually, I have not. Okay. What do we do? I think let's break for lunch, and maybe shall we do 15 minutes before you do the labs? Maybe we can have 15, 20 minutes of lecture, because there's some stuff for the lab today that I was hoping to cover that I haven't. Okay, I think I got too drawn into the whole Fourier stuff. But the thing is, showing all these Fourier transforms, if the basics are not viewed in the same way that we need to understand this, it'll be even harder. So let's meet here at 2, or is 2 fine? Okay, so let's meet here at 2, and then we can maybe do 2:20. You can go to the lab, okay? Because I feel the lab's. We finished lunch earlier. Does anyone have a problem coming back earlier than 2? Okay, so maybe 10 to 2. That'll give me about 15-20 minutes, and then 2:10 or so you can go to your lab, because that you will need for one of the lab exercises. Okay.